Linear combination circuits, which are also called summing amplifier. An extremely important circuit, a very practical circuit actually, used in many ADCs, DACs, analog to digital converters, digital to analog converters, and many other circuits. This specific combination of operational amplifier and inputs. So what is the basic idea behind linear combination circuit or summing amplifier? This is the basic idea right here, that the output is equal to the combination of all the inputs, and all the inputs are connected through different resistors to the inverting input terminal. So the output is the linear combination of all these inputs, and each one will have its own specific gain. So A1, A2, A3, A4 all the way up to AN. That's the basic idea of a linear combination circuit, that you're combining all the inputs to produce the equivalent or produce the corresponding output through an individual gain. Now these individual gains can be same. So if they are same, then we have one total gain for the whole circuit. If they are different, then each input will be multiplied by that specific gain and added to the next input multiplied by the individual gain of that, and all that addition is going to produce the output voltage. How do you analyze the circuit? The similar way you analyze the inverting amplifier. You have an inverting amplifier, you had only one input, now you have multiple inputs, but you still apply KCL at virtual ground. This is your virtual ground, right? Because this is grounded, this is your bias compensation resistor, it is not going to affect in our analysis. So you have the 0 volt appear at the positive input, and then virtual ground will appear at the negative input. So when you apply KCL here, I1 plus I2 plus I3 all the way up to IN is equal to IF, this equation. And then you are going to apply Ohm's law, of course. IF is negative V naught. Let me erase this thing. Oops. Okay, so IF is negative V naught, 0 minus V naught over RF, and of course each input current is going to be V1 minus 0 over R1, V2 minus 0 over R2, and so on and so forth. This is going to be your equation, and from that equation you can calculate what is V out, which will be negative RF over R1, V1, RF over R2, V2, so on and so forth. So RF over R1, RF over R2, RF over R3, they will be A1, A2, A3, and since it is an inverting amplifier, you have a negative sign here, right? So the output is going to be inverted with respect to the inputs. Now most of the time, if you want the output to have the same sign as the input or the inputs, then all you need to do is you need to connect an inverting amplifier over here. So if you connect an inverting amplifier over here, negative, positive, such that the gain of the inverting amplifier is 1, then the output of this inverting amplifier is going to be what? The output of this, but it is going to invert the phase of this. So let's say if this is V out 1 and this is the total output, then V out will be equal to V out 1, since the gain is 1, RF over R input is 1, but the output will be opposite of the input. So if this is negative, since this is negative already, as you saw, this is a negative sign, then negative of negative is going to become positive at the output. So this is one way that you basically make the output to be positive instead of having the negative output. As you will see, of course, there's an example where you will see this type of thing. So actually there's a circuit that I was going to show you that I explained. So this is the same circuit to change the phase of the output as I explained. So this is the example. Go over this example. There's also a very good example in the textbook. Go over that example as well to see a different way to use the in the linear combination circuit. But go over this example, and the circuit is over here that correspond to that example. Again, if you don't understand, then we can discuss it, but at least first you can go over this. And the last topic of this chapter is a closed loop differential amplifier. Now remember, operational amplifier is a differential amplifier in its open loop configuration. That is, whatever voltage you apply between the input and the inverting and non-inverting input, in the open loop configuration, that voltage is amplified at the output, right? A times VD. But again, that does not really help us because of the extremely large gain of the operational amplifier. Any small change in the input differential voltage is going to just saturate the output, so it doesn't really help us. So we create the differential closed loop differential amplifier. So we have two inputs, V naught, V input, the V1 and V2. V1 is connected to the positive input, V2 is connected to the negative input through the resistors. And I'm just renaming this resistor R1, or not renaming, I'm just showing it clearly because these values are so small. So this is R1, this is R3, R2, and R4. Now the goal of this circuit is that the output basically should be equal to A1 V1 minus A2 V2. That is the goal of the circuit. That is, it should be equal to the difference of the two input. Each input will be multiplied by its own gain and then subtracted, and the output should be equal to that. That's the goal of the circuit, closed loop differential amplifier. So when you do the analysis, the first thing we do is we find out what is the voltage at the non-inverting input right here, and that voltage can easily be figured out because the current will be flowing in this direction. It's not going to go in here. So these two will appear in series with each other, and you apply the voltage division to find out what is the voltage at the non-inverting input, which will be R2 over R1 plus R2 times V1. And this voltage will appear at the inverting terminal as well, V positive. So now you're gonna go ahead and apply KCL at the inverting terminal. Here, let's say this node is A. So you're gonna write down I3 equals I4, and I3 is V2 minus VA. VA is V positive, so V2 minus V positive over R3, and then VA minus V out over R4, again V positive minus V out over R4, right? And this analysis is given right over here. V2 minus V positive over R3 is equal to V positive minus V naught over R4. And then you can simplify this. As you can see, I am simplifying it, and the final result you're gonna get is V1, A1 times V1, where A1 is R2 over R1 plus R2, 1 plus R4 over R3 after the analysis, after the simplification, and you can see the simplification, minus R4 over R3 V2, and R4 over R3 is A2. So your final result is gonna be A1 V1 minus A2 V2, what we set to get from this circuit. Now, if you want to have the same gain for both the inputs such that your output will be V out equals A times V1 minus V2, if A1 and A2 are A, or ACL I will call it, ACL, closed loop gain, then your amplifier is going to be a balanced amplifier, differential amplifier. It is called a balanced differential amplifier, and you just have to meet this condition. That is, R1 will be equal to R, R2 will be equal to A times R1, A or ACL, whatever you want to call it, R3 will be equal to R, and R4 will be equal to A times R3, and since R3 is R, that's going to be AR, R2 is AR. Okay, so if you want a balanced amplifier, then R1 is R right here. The value of this is going to be R, and R2 value is going to be AR. R2 value is going to be right here, is going to be A times R, and R3 is going to be R, and R4 will be A times R. Whatever gain A you want from the circuit, that is, right? If you want 10, then, and if R is 1 kilo ohm, then this is 1 kilo ohm, this is 10 kilo ohm, this is 10 kilo ohm, this is 1 kilo ohm. And once you do that, you can plug those values here, and you will see that you will have the same gain value A1 and same gain value A2. So you're gonna get basically V naught is equal to A times V1 minus V2, and the differential amplifier is gonna be called a balanced differential amplifier. And this finishes up this chapter.